For this set of mini lectures, we are going to talk about the outer planets, or the outer worlds. Beyond the orbit of Mars, the low temperature of the original solar nebula allowed condensing bodies out past Mars to capture hydrogen and hydrogen-rich gases. This, together with the incredible amount of material that's at the edges of our solar system, led to the creation of our 4 large Jovian planets. We've got Jupiter, Saturn, Uranus, and Neptune. These planets are composed mainly of gas and liquid hydrogen. These planets don't really have a solid surface to speak of. The dwarf planets, Pluto and Eris, out past Neptune, are exceptions to these rules and resemble the ice and rock makeup of the giant planets' larger moons. The moons of our outer planets form families of little miniature solar systems, although individually each moon represents a unique combination of size, structure, and appearance. So let's start with Jupiter, the largest of all of our planets, the king of the planets. Jupiter is the largest planet both in diameter and mass. It's more than 10 times the Earth's diameter and 300 times the Earth's mass. So here's our Earth for comparison to Jupiter. And we have Jupiter's Great Red Spot, which is this large, essentially hurricane that's been on Jupiter for more than 300 years. And that giant spot is about the size of Earth itself. Jupiter's signature are its dense, rich colored parallel bands that you can see all over the surface. And its atmosphere is mainly hydrogen, helium, and a few other gases. What we see of Jupiter's atmosphere are the cloudy banded structures of Jupiter, and that's what we're seeing right here. These clouds appear to be particles of water, ice, and ammonia compounds. The bright colors of the clouds come from complex organic molecules or compounds of sulfur or phosphorus. Jupiter rotates once about every 10 hours, pretty rapid rotation, and this fast rotation leads it to have what we call an equatorial bulge. That means that Jupiter is actually a little bit bigger at its equator than it is at its poles. So the radius of Jupiter isn't constant all the way around. The radius, the distance from the center of the planet to the edge, is a little bit bigger at its equator than it is at the poles because it's spinning so rapidly. We see that sometimes really massive stars will be like that too. Jupiter's average density is about 1.3 grams per cubic centimeter. That's much, much less than our Earth's average density. This indicates that the interior of Jupiter is composed of very light elements, mostly gases. Its interior becomes increasingly dense with depth, and the gas in Jupiter's outer layers turns to liquid hydrogen at about 10,000 kilometers down. So here we have a column of gas, and we can divide that column up into segments. Every little segment, if there's no gravity, every little segment will have the same density. Okay, that's the mass per unit volume. But then if we have gravity, we're thinking about gas, the material that's closer to the center of the planet is going to experience a greater gravitational pull than the material that's just a little bit further away from the center of the planet. And then the layer of the atmosphere that's just a little bit further away from the center of the planet will feel less of a gravitational pull, and so on. So that means that the material that's deeper down in the atmosphere, closer to the core, this gas layer, that material is going to be more dense than all the material that gets stacked up. And just when you think of, especially, we could relate this to like the pressure that you feel in the ocean or underwater. The deeper down you go in the water, the more pressure your body will feel, because also of all that weight of the material on top of you pushing down and being pulled down also by Earth's gravitational pull. So the material is going to be denser when you're closer to the center of the planet than when you are at the upper layers of Jupiter's atmosphere. Under all of that pressure that hydrogen gas turns into liquid hydrogen. And then even deeper still, under more pressure, that hydrogen, liquid hydrogen, turns into what we call liquid metallic hydrogen. That material is under such pressure and experiences a greater density that that material becomes electrically conducting. And that's why we call it liquid metallic hydrogen. It becomes electrically conducting just like the liquid metal interior of our Earth. Even though it's just hydrogen, it starts to gain some properties of liquid metals. And so whenever that material stirs up and spins up and convects, it can generate an electric field, and as a byproduct, a magnetic field. So Jupiter has a large scale magnetic field. It does have an iron rocky core, which is just a little bit bigger than the Earth at the center of Jupiter. But then above that, we have the layer of liquid metallic hydrogen, and then we have a layer of liquid hydrogen, and then the outer gaseous layer of hydrogen that creates those beautiful banded clouded structures that we see whenever we see images of Jupiter. Jupiter has a core temperature of about 30,000 Kelvin. It actually emits more energy than it receives from the sun. The planets generally emit radiation in infrared, so it's not emitting radiation in the visible. When we see Jupiter, what we're seeing is light being reflected off the surface of Jupiter. That light is light from the sun being reflected off the surface of Jupiter, and that's what we see with our eyes when we observe Jupiter. So this intense heat of Jupiter of about 30,000 Kelvin is due to heat left over from its creation in the early solar system. And the planet may also still be kind of condensing and shrinking in size, and that converts gravitational energy into heat. So yeah, Jupiter is far enough away from the sun that it's giving off more energy than it receives from the sun. The atmosphere of Jupiter is convecting, just like the Earth's outer liquid metal core. And in that convecting layer is where we're going to generate magnetic fields, and also creates the pattern of clouds that we see on Jupiter's surface. So what do I mean by convection? Well, heat from within Jupiter carries gas to the top of the atmosphere. And then that gas cools when it reaches near the top of the atmosphere. And then when it cools, it becomes less dense and it starts to fall back down. It starts to fall back down towards the center of Jupiter. And so then you create these big overturning fluid patterns that we call convection cells. So hot material is rising to the top of the atmosphere, it cools, and then it turns over and falls back down towards the center of Jupiter again. There's something called the Coriolis effect, which also lends to Jupiter's beautiful bands of clouds. The Coriolis effect happens whenever you have fluid, so gas is a fluid, and the material is spinning. And so what happens is that that rising material from deep within Jupiter rises to the surface. And because of that rising and the fact that Jupiter is spinning, the Coriolis effect turns the rising and sinking material gases into these powerful jet streams of about 300 kilometers per hour that are seen as the clouded belts or clouded bands of Jupiter. And the different layers of the bands of clouds on Jupiter are going in opposite directions, okay? So you've got the warm material rising from deep within Jupiter because of the spinning of the planet. That can cause one stream of those clouded banded structures to go one way, and it can cause another band of those clouded structures to go the opposite way whenever the material starts to cool and sink back down, okay? And then that creates the alternating bands of clouds on Jupiter. Some of them are going to the east, some of them are going to the west, and they can be booking it. These winds and these streams can be moving at speeds of about 300 kilometers per hour. That's pretty intense. Some of the most intense weather in our solar system we can find on Jupiter. Here we see a close-up again of Jupiter's great red spot, okay? And you can see that it kind of lies along here, along these clouded banded structures. You can think about this great red spot as being this large hurricane, and it has persisted for more than 300 years, for as long as we have turned telescopes to the sky to observe objects in our solar system. The thing that causes Jupiter's great red spot is something called the Kelvin-Helmholtz instability. This is part of fluid dynamics, the study of fluids, and it's kind of part of what I did for my PhD too. Okay, so what happens? We have something called a velocity shear. That's velocity moving in different directions along a boundary. That velocity shear would be present between two consecutive banded clouded structures, where one band of clouds is going one way, the other band of clouds is going another way. So at these shear interfaces where you've got motion going in opposite direction, you can create an instability that creates these giant vortices, just like the great red spot that we see on Jupiter. So this instability occurs in fluids of high density where there are streams of winds moving in opposite directions. Those are our banded clouds on Jupiter. So here we have an example of this. This is from a simulation that you can type up in a computer program in order to create one of these Kelvin-Helmholtz instabilities. So in green, we have a structure of material, of fluid that's flowing to the right. And then we have in blue material that is flowing in an opposite direction. Okay, and what happens at the interface of those two regions of material that are flowing in opposite directions, you set up these little vortices. Well, actually big vortices, it turns out, in the case of Jupiter. You set up these big vortices, and these vortices can turn into swirling hurricane-like storms. And that is exactly what's happening on Jupiter. And Jupiter's poles are really interesting. Jupiter also has vortices, hurricanes, at its north and south poles. So we only recently got to see these really cool images of Jupiter's poles taken by a spacecraft called Juno, which is orbiting around Jupiter's north and south pole. It was unexpected that we would see these beautiful vortices like this on Jupiter's north and south poles. So Jupiter's north pole, this is an example of these vortices at Jupiter's north pole. You have a central vortex that is surrounded by 8 little vortices all around the edges. They're persisting and they're moving around this central vortice. But it's different in the southern hemisphere. You've got one central vortice surrounded by 5 smaller ones. For some reason, you know, the material is behaving a little bit differently at the North Pole than it is at the South Pole. That's okay. We know planets are not symmetrical. There's different dynamics happening all over this massive planet that could contribute to the setup of these vortice patterns that are different in different hemispheres and in different places. So these images were highly processed in order to really pick out these swirling vortices here. This is the actual picture of one of those poles that you would see in visible wavelengths of light. And so we've got the central vortices surrounded by these smaller ones at the pole, and then you even see other little vortices that are popping up here too. So Jupiter has some crazy weather, way more crazy than any of the weather we have on our planet. Jupiter also has a very strong magnetic field, much stronger than the magnetic field of Earth. So convection in the deep metallic liquid hydrogen layers of Jupiter, coupled with Jupiter's rapid rotation, are what creates this powerful magnetic field. To give you an idea for scale, Jupiter's magnetic field is 20,000 times stronger than that of our Earth's. And Jupiter's magnetic field is the largest planetary magnetic field in our solar system. And Jupiter's magnetic field allows it to have auroral activity. We already talked about the aurora on the Earth. Same thing is happening for the aurora on Jupiter. Jupiter has a lot of moons. This slide I have to update because Jupiter no longer has only 63 moons. We think Jupiter now has 79 moons. We keep on discovering more and more moons as we observe Jupiter for a longer period of time. So this number changes all the time. The four innermost moons are called the Galilean moons. Those are the four innermost and four largest moons of Jupiter. Here are those four Galilean moons in comparison to our own moon. We've already talked a little bit about them, but except for Europa, so our Galilean moons are Io, Europa, Ganymede, and Callisto, here listed in the order that they are away from Jupiter. So Io is the closest one in to Jupiter, and Callisto is the furthest Galilean moon out from Jupiter. Except for Europa, all of these moons are bigger than our own moon of the Earth. And they're formed in a similar process to the formation of our solar system. And the density of these satellites decreases with the density from Jupiter, kind of like how the planets in our solar system generally tend to decrease with density as we get further away from the sun. So we had our proto-sun, that around which we had the disk of material from which our planets formed. Here we had the proto-Jupiter, and around the proto-Jupiter we had a disk of material from which the Galilean moons formed. Saturn is the second largest planet in our solar system, the next largest after Jupiter. It has a diameter of 10 times that of the Earth and a mass about 95 times that of Earth's mass. Its average density is 0.7 grams per cubic centimeter. Its average density is less than that of water. So you can actually float Saturn in a giant bathtub if you could create a bathtub that large in our solar system. Its low density, like Jupiter, suggests a composition mostly of hydrogen, but Saturn looks different from Jupiter. Its temperature is low enough for ammonia gas to freeze into cloud particles that veil its atmosphere. Okay, so there are some bands on Saturn as well, but not those vivid, distinct bands of clouds like we see on Jupiter. But Saturn also has a beautiful set of rings, which you'll learn about in another mini lecture. The interior of Saturn is not too different from that of Jupiter. It also radiates more energy than it receives from the sun, and it has an inner rocky core, and then we think maybe it has a layer of water, and on top of that, this liquid metallic hydrogen where the pressure is so great that the hydrogen can turn from a gas into a liquid, but also a liquid that has electrically conducting properties such that you can stir it up and it generates an electric field, which as a byproduct creates a magnetic field. So Saturn has a large scale magnetic field as well. We talked about the polar vortices on Jupiter. Saturn has a polar hexagon. Yes, it's really cool and really weird, but if you look at Saturn's North Pole, it looks like a hexagon. The cloud shapes look like a hexagon. So we've got 6 sides as a hexagon here. What causes it? It's a result of the fluid processes inside Saturn. So Saturn's rotating, and the gases inside Saturn are convecting just like they are in Jupiter. And so the motion of all that material together results in this cloud pattern that looks like this hexagon. And so, you know, astronomers are working on computer simulations to try to better understand how Saturn can create this hexagon pattern at its poles from motion of the fluid. And when I say fluid, I don't just mean something that's like a liquid like water. Gas, air, atmosphere behaves like a fluid as well.